Hello, welcome back. So, in the previous part, we have seen some of the concept related to the beam reactions because the application of moment that we are going to use is largely in calculating the beam reactions. So, we have seen what are the conditions of equilibrium. We have seen how do we draw the free body diagram, types of reactions, types of supports. So, now we will calculate the beam reactions. But before that, we will see what are the types of load that are likely to occur on the beam and as well as their representation. How do we represent those loads? So first load will be that comes on the beam. It is known as point load or concentrated load. Well, this point load can be, for example, in this case, you can see there is a beam which is supporting another beam. So this beam is passing, this beam looks like this one. So this is the beam like this. And this beam is passing through this beam like this. Something like this. So actually we will see that this beam is passing at this particular point. You can see here, this is the particular point, this is passing at this. So as it is passing through one point of the beam only, so we can consider the load of this beam as the point load. Or if on this beam, if say one person is standing, here, then the load of that person will also be considered as the point load. So that is the point load. And generally we represent point load by with a single arrow. So it may be downward or upward. Then second load is known as uniformly distributed load. So uniformly distributed load, as the name suggests, this is a kind of load which is uniformly distributed over a length of the beam. So for example, if we take an example like this is the beam and it is resting on the column, say it is resting on the column. And if this beam is supporting the weight of the plate or the slab, so as you can see, the slab is resting on the whole beam. So the load of this slab can be considered as the uniformly distributed load. So this is the representation of the UDL. So this is, and we generally express this UDL like this, 3 kilonewton per meter, which means the load of this, this UDL intensity is 3 kilonewton per meter, which means load per meter length. So per meter length, load on the beam is 3 kilonewton per meter. So that is the representation of UDL, which is uniformly distributed load. Another load which generally occurs on the beam is UVL, which is uniformly varying load. There are some loads which may vary uniformly along the length of the beam. For example, in this case, you can see the load intensity of the load or load intensity at point A is 0, while the load intensity at point B is W kilonewton per meter. So you can see the variation of the load is uniform. So that is why it is called uniformly varying load. So this variation may be in like the triangular variation, or it may be trapezoidal. So this is the case of triangular load. And this is the case of trapezoidal. So in this case, trapezoidal variation is occurring for the load. Sometimes UDL is also expressed like this. Okay, in some cases it may be expressed like this and the intensity will be same. So sometimes it is like this or like this. We can represent this. So these are the load that generally comes on the beam. So now we will take an example to see how we can find out the beam reactions. So now this is the example in this. we have to find out the reaction. So you can see this is the beam AD and it is supporting a UDL of 20 kilonewton per meter over a length of 3 meter, and also it is subjected to a vertical downward load of 50 kilonewton, and this is the point load. So this is point load and this is UDL. So this beam is supporting the UDL and point load, and this beam is also known as simply supported. Why? Because one end of this beam is hinged and the other end of this beam is roller supported. So such kind of beam which is supported by hinge and roller, in that case such kind of beam is known as simply supported beam. So now we have to find out the reaction which is being offered by this beam and what will be the magnitude of that reaction. So first of all, our first step is to make the free body diagram of this beam. So we are showing this beam as a single line, and the reaction offered by this hinge will be 2. So one reaction will be say RL, left hand side reaction, and one reaction will be RH, which is horizontal reaction. Similarly, up to this length there is a UDL, and the intensity of UDL is 20 kilonewton meter. Similarly, there is a point load which is 50 kilonewton, and at point D there is another reaction which we are calling as RR. So right hand side reaction which is RR, left hand side vertical reaction which is RL, and the third reaction is RH, which is the horizontal reaction. So this beam is offering 3 reactions, and we have to find out what will be the magnitude of the reactions because of these 2 loads. So now, first of all, we will assume that our system, our beam is in the equilibrium. So we will write here, assuming the beam in equilibrium. Now, why we are assuming? Because once we assume that our beam is in the equilibrium, then we will be able to use the equilibrium equations. So now we will say applying equilibrium equations. As you can see, this beam is shown in the 2 dimension. So therefore, we will be having 3 equations. One, summation of H is equals to 0, or we can write as Fx, summation of Fx is equals to 0, or we will write summation of V is equals to 0, which means summation of all the vertical forces should be 0, or we will write as Fy is equals to 0. So either we write summation of H is equals to 0, or we write summation of Fx is equals to 0. Both are same. Similarly, either we write summation of V is equals to 0, or we simply write Fy is equals to 0. Then this equation will become first equation, this is second equation, and the third equation is summation of M is equals to 0, which means moment. So we will write here summation of M is equals to 0, which becomes our equation 3. So now first we will use equation 1. I will write here using equation 1. So as per equation 1, it says summation of Fx is equals to 0, which means all the forces in x direction will be equals to 0. So x direction is this one and y direction is this one. So in the x direction, you can see there is no force. There is no force. I will write here no horizontal force. So therefore, this reaction will be 0. So I will write here hence RH is equals to 0. Why? Because there is no horizontal force in the beam. Similarly, now we will use the second equation, equation 2. So I will write here using equation 2. So as per equation 2, it says summation of Fy is equals to 0, which means summation of all the forces in y along the y axis, which means vertical axis. So all the vertical forces, their algebraic sum will be equals to 0. So which means all the vertical force. So what are the vertical forces in our beam? Well, there are two reactions, two vertical reactions. There are also forces, and there are UDL, which is downward vertical force. So this is also a force, and the point load, which is downward. So there are four forces. So we have to find out their algebraic sum. So RL is, now we have to remember, upward force will be taken as positive and downward force will be taken as negative. Okay, so we have to remember this. So now it says RL, you can see RL is vertically upward, so we will take RL as positive. Similarly, this UDL, now UDL is 20 kilonewton per meter, and it is at a length of 3 meter, and this is 1 meter, this is 3 meter, and this is 1 meter. So 20 kilonewton per meter. So this UDL is spreading at a length of 3 meter. So the total load because of this UDL will be 20 into 3. So you can see 20 for 1 meter length, it is 20. And for 3 meter length, total load will be 20 into 3, which is 60. And you can see this is downward. So we will take downward load as negative 20 into 3. So this becomes the negative. Similarly, the next point load, it is again downward. So we will take it as negative 50. Then we have the another reaction, which is on the right hand side, RR. So we will take this as positive RR because it is pointing upward. Now these are the forces, vertical forces. There is no other vertical force, so we will equate this as 0. So we can write this as RL plus RR equals to 20 into 30, 60 and 50. So this becomes 110 kilonewton. So this becomes our equation 4. So now I will erase some to write more. Okay, so now we have used equation 2. Now we will be using equation 3, which is summation of m is equals to 0. Now this summation of m is equals to 0 means, I will write here, it means the sum, the algebraic sum of, it means the algebraic sum of moment of all the forces should be 0. So at any point we find out moment of all the forces, it will be 0. So now first what we will do is we will write taking moment about, say this is point A. So this is point A. So we will be taking moment about A. Taking moment about A, which means about this point. So you can see RH force is passing through point A. So there will be no moment because of the RH. Similarly, the force RL is also, I mean the line of action of RL is also passing along the point A. So the moment because of the RL will be 0. Now the moment due to the UDL. Now the total UDL is 20 into 3. Now, but where it will act? It will be acting at the mid of the length. So if it is spreading along the 3 meter length, then it will be actually concentrating at half of this length. So I will write here 20 into 3. So that is the total magnitude of the UDL. And where it will act? It will be acting at mid of the length. So the distance, perpendicular distance from this point to this point will be 3/2. Okay. Now, as you can see here, this is actually rotating like this. So it is clockwise. So we will be taking this as positive. Similarly, moment due to this force, it will be 50 multiplied by the perpendicular distance. So we will see here. So distance between C and A, because point load is acting at C point. So distance between AC is 3 plus 1, which is 4 meter. So again, you can see here the moment created by this force will also be clockwise about this point. So positive moment will be there, which is plus 50 multiplied by 4. Okay. Now the next is reaction RR. This reaction RR is upward. So about this point, this force will be rotating like this, which is anti-clockwise. So minus RR multiplied by the total distance, this 3 plus 1 plus 1. So this becomes 5. So now we will equate this with the 0. So now by solving this equation, I will clear the space first. So by solving this equation, we can find out RR as equals to 290 by 5, which is further equals to 58 kilonewton. Okay, so this is our value of RR. Now similarly, we can find out value of RL. You may remember that equation 4. So equation 4 was RL plus RR equals to 110. So this was our equation 4. So using this equation, we will put the value of RR and we will simply calculate the value of RL. So it will be 110 minus 58, which becomes 52. So that is the reaction of RL, and this is the reaction of RR. So this is how we find out the reaction. So ultimately, we can write here RL as 52 kilonewton and RR as 58 kilonewton, and RH is 0. So these are the reaction for this beam. Similarly, we can take another example, but we will solve this example in the next part. Thank you.